Welcome back. I hope you had a chance to try to write selection sort on your own, but if not, that's okay. Let me go ahead and show you my solution, and then we're going to do the runtime complexity. So here's my Python code. It takes as input a list, and then this code, of course, is going to modify that list. Now remember that when you send lists into functions, they are sent as addresses, and so when we modify the list in this function, we modify the entire list. All right, so let's go through and see what's happening with the code. So there's this first for loop here that says for I in range length of the list minus 1. Okay, so I is going to be an index 0, 1, 2, 3, 4 up into the length of the list minus 1. Why minus 1? Well, at the very end of the list, remember the way selection sort works is I find the smallest element of the list and I put it into the first position. I find the second smallest item in the list, I put it into the second position, and eventually I get to the second to last item, and then the last item is guaranteed to be the largest item. So I only have to go to the minus 1 position. Okay? So first iteration through, what's my job? My job is to find the smallest item in the list, and I'm going to swap that into the first position. So how do I do that? Well, I'm going to say, all right, let's say that the smallest value is the first element in the list, and then I'm going to compare that to every other element in the list, searching for something smaller, 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 and then I'll do the swap. So in this step right here that I've highlighted, I've set the min val to be the ith element in the list. Okay, so when I is 0, I just say, okay, for right now, that's the minimum value. And I need the index, so I'm going to hold on to that index right here in index equals smallest. So now my job is to go through the rest of the list and find the smallest element. So I've initialized to be the first element. And now for j in range I plus 1 to the length of the list. So let's see. Why I plus 1? Well, I've already established that I've initialized min val to be the ith element. So now I'm going to look at the second, third, up into the last element. So here I do have to go to the very end because I'm going to go to the very end. And for each one of these, I'm simply going to compare the jth element to what I initially set the min val to be. If I find something smaller, I'm going to update the min val, update the index, and then keep going. So if the list sub j is less than the current min val, I initialize that here to be what's in the 0th position, then update the min val to that position and update the index to be j. All right, spin through this. Notice that these for loops are nested. Spin through this for loop. I go through the entire list, and at the end of that, I have the minimum value and the index of the minimum value for the entire list. Now, what do I want to do? That's somewhere down here, let's say. I have to now replace it with the first, what's in index 0. So I'm going to do a swap of those two elements. That's this little bit of code here. So I'm going to set temp to be what's in the list sub I. For initially, that's 0 for the first iteration of this for loop. I'm going to set the ith element to be the min val. Good. And then the list of where it was is temp, which is what was in the original position. So that's just a little bit of 3 lines of swapping code. Okay, notice that this swapping code is embedded inside of this for loop here. Yeah? So I do that for I equals 0. I find the smallest element on the list, and I swap it. Now, next iteration of the for loop, I is now 1. I'm going to search from 2 to the end. So now I'm going to find the second smallest item in the list, and I'm going to swap it with position 1. And then I is 3, and same thing, until we get to the very end. So you can see I have these 2 nested for loops. This is doing that overall, each step of that algorithm that we outlined in the previous segment, and this is doing the searching of the smallest element in the sublist that we care about. Good. So let's do the runtime analysis. So back of the envelope, you can see some basic structure here. So where is the cost? First of all, the cost is going to depend on the length of the list, n. Okay? I've got a for loop here that's going to run through n minus 1 times, and I've got a nested for loop here. All right, so let's see. Let's ignore this for a little bit. So I've got in this external I for loop, I've got 2 statements. Let's say that has a cost of C1. I have 3 statements here, which is the swap. Let's say that has a cost of C3, some constant. Okay. How many times am I going to have to evaluate those 2 lines of code and those 3 lines of code? Well, it's going to be dictated by that for loop right there, which is the length of the list minus 1. So that whole cost is going to be n minus 1 times C1 plus C3. So the cost of initializing and the cost of swapping. Now inside of that though, I've got another for loop. Yeah? And so now we've got to ask ourselves, well, how many times did that for loop run? Well, it's not so straightforward, right? It's not always 1 to n. It's I plus 1, where I depends on this external. So on the first time through the loop, it'll run n minus 1 times, right? Because it goes from 1 to the length of the list. But the second time through, when I is 1, it's going to run n minus 2, and then n minus 3, n minus 4, down to 1. So this inner loop has some cost, C2, associated with the conditional and setting these variables, whatever it is, we don't care, some cost, C2. But it's going to run, well, the first time through it's n minus 1, the second time through it's n minus 2, as we just decided, because each time I'm updating that little I. And so that means on each iteration of this for loop, this one is running a little tighter, little tighter, little tighter. Okay? So now we got to do a little calculation here. I had the external n minus 1 times some constants, and then I've got to sum up n minus 1, n minus 2, n minus 3 down to 1. So let's see what the cost is. So it's n minus, and by the way, let's remember, we don't care about the multiplicative constants. So I'm going to go ahead and ignore C1, C2, C3. I just put them in there to remind ourselves that there's a cost associated. All we care about is there's some cost. I don't care that this may be a little more expensive than this. So there's the external n minus 1 cost. That's the initialization and the swap. And then there's a cost every time we run this for loop. The first time through it's n minus 1. The second time it's n minus 2, all the way down to 1. And so now I've got to sum all these up, and that will tell me the cost of running the entire selection sort on a list of length n. All right, so how do I sum these things up? Well, let me just do a little bit of rejiggering of the values here. Let me take that minus 1 that was here and just put it over here. And the reason I'm going to do that is now I've got n plus n minus 1 plus n minus 2 down to 1, and then I'm going to have a little off by 1 error here, which we're not going to care about because that's a constant. So this is a nice little closed, simple expression, the sum of the first n numbers. Okay? So if you haven't seen that before, let me show you how you compute the sum of the first n numbers. Imagine I asked you to sum the first 10 numbers. Well, you can do the obvious thing. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and so on and so forth. You can sum them up. Or you can notice something clever. If I take the first number and the last number, they sum to 11. If I come in 1 and come in 1, those two numbers sum to 11. 3 and 8 sum to 11. 4 and 7 sum to 11, and 6 and 5 sum to 11. Why is that, by the way? Well, because here I'm incrementing by 1, and here I'm decrementing by 1, and so the sum stays the same. This has some sum. If I add 1 and decrement 1, those two numbers must have the same sum, since they're all in order. So the sum of the first 10 numbers is 11 plus 11 plus 11 plus 11 plus 11 5 times. So it's n plus 1 times half the length, n over 2, no matter what n is. Okay? So the sum of the first n numbers is n plus 1 times n over 2. And again, I can drop that minus 1 because that's just a constant. It doesn't depend on n, and so it doesn't do me any harm. Yeah? Now, what's this? Well, it's n squared over 2 plus n over 2. So let's just write that out. So n squared over 2 plus n over 2. Okay. Now, remember when you're doing runtime calculations, you are doing worst case, assuming n gets very, very large, and you don't care about additive constants. That's the minus 1 we just dumped. And you don't care about multiplicative constants. So I don't care if it's n squared over 2, n squared over 3, n squared over 4. In practice, that matters, of course. But in terms of runtime complexity, big O notation, I'm going to ignore those multiplicative constants. So my runtime is n squared plus n. Now, one more thing that we haven't done, but here it comes, is when you have, let's remember, by the way, that n squared is much more costly than n. This says that the runtime grows linearly with the input. This says that it grows with the square of the input. So when you have something that is n squared plus, not times, but plus a smaller term, you can ignore the smaller term. And so we say that something that runs in n squared plus n is O of n squared. Why is that, by the way? Why do I ignore something that depends on the size of the input? And the reason is that as n gets really, really big, this term dominates, and that n term is very, very small. And you can convince yourself of this. Start writing out values of n and their square, and you will see when you get to, for example, 100, you've got what? 100 squared, 10,000 compared to 100. When you have 1,000, you've got 1,000 squared, 1,000,000 compared to 1,000. So that linear term is actually relatively small compared to the square term. And so we ignore the smaller additive terms and just grab onto the largest term here, and that's what the big O notation is. So selection sort runs in O of n squared. Is that good or is it bad? Well, I don't know. It depends on n. But generally speaking, something that scales with the square is going to start to get costly. We just saw that. Every time I increment my size of my list by a small amount, my cost increases by the square of that amount, not linearly, not logarithmically. So this is going to start to get pretty expensive at some point. But it's a good sort algorithm. It's actually relatively easy to write, a couple lines of code. Nothing particularly fussy, and it works. So can we do better? Well, we'll see in a little bit. Okay, so that's selection sort. And what we're going to do following this segment of the lecture is we're going to see a couple of other sorting algorithms. I'm going to do the same thing. I'm going to describe the algorithm. We're going to write a little bit of Python code. I'm going to encourage you each time to do that on your own. It's a good exercise. And then we're going to do the runtime complexity, which will continue to be a good exercise in making sure we understand big O notation. All right, so we'll come back with a new sorting algorithm in a few minutes. I'll see you then.